Good day everyone. Our subject for today is Mathematics 10 3rd quarter week 1 day 1 to 5. I'm your teacher, Ruel R. Rosales Jr. Our topic is all about fermentation. But before we proceed, let's read our learning targets. I can define fermentation. Apply the fundamental principles of counting, and illustrate the fermentation of objects. So what is fermentation of objects? A fermentation of n objects taking R at a time is an arrangement of R of the n objects in a specific order. The symbol for this number is P, the quantity of n R. Remember, first, a fermentation is an arrangement or sequence of selections of objects from a single set. Second, repetitions are not allowed. Equivalently, the same element may not appear more than once in an arrangement. Third, the order in which the elements are selected or arranged is significant. Example 1. The number of photographs of 10 friends taking 3 at a time. Calculate P, the quantity of 10, 3. P, quantity of 10, 3 is equal to 10 times 9 times 8 is equal to 720. Note that you start with 10 and multiply 3 numbers. A general formula using the multiplication principle, P, quantity of nr is equal to n times quantity n minus 1 times n minus 2 until n minus r plus 1. Note that there are r consecutive numbers on the right hand side. Example 2. In how many ways can you choose a president, secretary, and treasurer for a club from 12 candidates? If each candidate is eligible for each position, but no candidate can hold 2 positions, why are conditions 1, 2, and 3 satisfied here? P, the quantity of 12R is equal to 12 times 11 times 10 is equal to 1,320. Condition 1 is satisfied because we have a single set of 12 candidates for all 3 positions. Condition 2 is satisfied because no one can hold more than 1 position. Condition 3 is satisfied because being president is different than being treasurer or secretary. Factorials. Example. In how many ways can you arrange 5 math books on a shelf? 5 factorials is equal to P, quantity of 5 is equal to 5 times 4 times 3 times 2 times 1 is equal to 120. The number P, quantity of nn, is equal to n times quantity of n minus 1 times n minus 2 until 1 is denoted by the n factorial or n factorial. N factorial counts the number of ways that n objects can be arranged in a row. N factorial grows fast. N factorial is equal to 1. 2 factorial is equal to 2. 2 factorial is equal to 6. 4 factorial is equal to 24. 5 factorial is equal to 120. 6 factorial is equal to 720. 7 factorial is equal to 5. 5,040. 8 factorial is equal to 40,320. 9 factorial is equal to 362,880. 10 factorial is equal to 3,628,800. 59 factorial is congruent to 1080. Truly, the number of particles in the universe. We can write our formula for P, quantity of nr, in terms of factorials, where P the quantity of nr is equal to n factorial over n, the quantity of n minus r factorial. Example 2. Evaluate 12 factorial. B. Evaluate P, the quantity of 12, 7. Solutions. A. 12 factorial is equal to P, the quantity of 12 is equal to 12 times 11 times until 2 times 1 is equal to 479,001,600. B. P, the quantity of 12, 7 factorials. Example 1. In how many ways can you arrange 5 math books on a shelf? 5 factorials is equal to P. The quantity of 5 is equal to 5 times 4 times 3 times 2 times 1 is equal to 120. The number P, quantity of nn, is equal to n times the quantity of n minus 1 times n minus 2 and so on, is denoted by n factorial or n factorials. Counts the number of ways that n objects can be arranged in a row. N factorial grow fast, n factorial equals to 1, 2 factorial is equal to 2, 2 factorial is equal to 6, 4 factorial is equal to 24, 5 factorial is equal to 120, 6 factorial is equal to 720, 7 factorial is equal to 5040, 8 factorial is equal to 40,320, 9 factorial is equal to 362,000, 1,880, 10 factorial is equal to 3,628,800, and so on until 59 factorial is congruent to 1,080, truly the number of particles in the universe. We can rewrite our formula for P, the quantity of nr, in terms of factorials. Example 2. Evaluate 12 factorial. B. Evaluate P, the quantity of 12, 7. Solution. A. 12 factorial is equal to 12, the quantity of 12 is equal to 12 times 11 times and so on, 2 times 1 is equal to 479,001,600. B. P, the quantity of 12, 7 is equal to 21 factorial over 12 minus 7 is equal to 4,709,001,600 is equal to 95. The permutation of n objects taking r at a time. There are two categories under these rules: permutation without repetition, permutation with repetition. Permutation without repetition. Example, how many 4-digit numbers can be formed from the digit 1, 3, 4, 6, 8, and 9 if repetition of digit is not allowed? Illustration. For 4-digit numbers, there are obviously 4 place values. Look at the figure below. The 6 digits 1, 3, 4, 6, 8, 9 are the possible choices for the 1,000 place value. We would say 1 is in the 1,000 place value. Since repetition of digit is not allowed, probably there are 5 possible choices of digits in the hundreds place values. We have 3, 4, 6, 8, and 9. But if 3 is in the hundreds place value, then the remaining 4, 6, 8, and 9 are the possible choices in the tens place value. And if we take 4 in tens place value, then there are 3 remaining possible choices in the ones place value. We have 6, 8, and 9. Using the fundamental counting principle, 6 times 5 times 4 times 3 is equal to 360. Using the notation P, the quantity of nr is equal to n factorial over n minus r factorial, using n is equal to 6 and r is equal to 4, 4-digit number. P is quantity of 6, 4 is equal to n factorial over n minus r factorial is equal to 6 factorial over 2, where 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1 over 2 factorials is equal to 360. Therefore, there are 360 different 4-digit numbers can be formed. Fermentation with repetition. This type of fermentation is the easiest to calculate. When a thing has n different types, we have n choices each time. Generally, choosing R or something that has n different types, the fermentations are n times n times until r times n to the power of r. In other words, there are n possibilities for the first choice, then there are n possibilities for the second choice, and so on. Multiplying each time, which is easier to write down using an exponent of r, where p is equal to n times r times is equal to n to the power of r, where n is the number of things to choose from, and we choose r of them. Repetition is allowed and orders matters. Example 1. In how many ways can a 5-item true-false exam be answered? The problems illustrates the fermentation replacement. Second, there are two possible answers which are true and false, so n is equal to 2. The answers will be arranged in a 5-item test, or r is equal to 5. Substituting the values of n and r into the formula, where p is equal to n times n times n times n times n is equal to n to the power of r is equal to 32. Therefore, there are 32 ways to answer a 5-item true or false exam. Permutation of objects with some alike. Example 1. How many words can we make by rearranging the letters of the word beer? The set beer is equal to bear, but we really have 4 letters with which to work. So let us start with the set brie. We arrange them in 4 factorials is equal to 24 ways. If we cannot tell the difference between E and E, there are both just E. Then the words group into pairs. Example, EEBR and EEBR group together. Both are the word EEBR. So see the illustration. Thus, the number of different words we can form by rearranging the letters must be 4 factorials is equal divided by 2 is equal 4 factorial times 2 factorial. Note that 2 factorial counts the number of ways we can permute the 2 a's in any given arrangement. In general, the number of fermentation of n objects with r of the objects identically in n factorial r factorial. Note that n factorial r factorial is equal to the quantity of n minus r. Example 2. How many words can be made from a rearrangements of the words banana? Banana is equal to ABN. The A is repeated 3 times. The N is repeated 2 times. The B is repeated once. Hence, the answer is 6 factorial over 1 factorial times 2 factorial times 3 factorial is equal to 60. Circular fermentation of n objects. Example 1. In how many ways can 4 boys and 4 girls can be seated on a cellular table such that A. Boys and girls sit on alternative positions. B. 2 boys sit together. Solutions. A. Boys can sit on the circular table in the quantity of 4 minus 1 factorial is equal to 3 factorial is equal to 6 ways. Consider the first boy, B1, as the fixed element and the remaining boys, B2, B3, B4 are arranged relatively to the B1. Look at the figure 1 shown below. The girls can be seated in 4 places, in between the 2 boys, in 4 factorial, so equals to 24 ways. So, the number of ways where boys and girls sit on alternative position is 3 factorials times 4 factorial is equal to 3 times 2 times 1 times 4 times 3 times 2 times 1 is equal to 144 ways. B. Temporarily treating 2 boys as 1. 7 persons can be seated on a cellular table in 7 minus 1 factorial is equal to 6 ways. Why 7? Because from 4 boys, we treat the 2 as 1. So we now consider 3 boys and 4 girls. However, these 2 boys can be arranged within themselves in 2 factorial is equal to 2 ways. Hence, the required number of permutation is equal to 6 factorial times 2 is equal to 1,440 ways. The fundamental principle of counting. If one thing can occur in m ways and a second thing can occur in n ways and the third thing can occur in r ways and so on, the sequence of things can occur in m times n times r times ways. First, multiplication principle of counting. If event A can happen in m ways and event B can happen in n ways, then event A and B can both happen in m n ways. Second, addition principle of counting. If event A can happen in m ways and event B can happen in n ways, then event A or B can happen in m plus n ways. Examples. To buy a computer system, Mr. Ford can choose one of 4 monitors, one of 2 keyboards, one of 4 computers, and one of 3 printers. Determine the numbers of possible systems that a customer can choose from. Solution. N is equal to 4 times 2 times 4 times 3 is equal to 96. Ben can take any one of 3 routes from school, S to the town, plaza, T, can take 5 possible routes from the town, plaza to his home, H. He does not retrace his steps. How many different possible ways can Ben walk from home? Solution. By the basic counting principle, the total number of routes Ben can take is 3 times 5 is equal to 15. 3. Catherine goes to her local pizza parlor and orders a pizza. She can choose either a large or a medium pizza. Has a choice of 7 different toppings and can have 3 different choices of crust. How many different pizza could Sarah order? Solution. By the basic counting principle, the number of different pizzas Sarah could order is 2 times 7 times 3 is equal to 42. So that's all for today, guys. Thank you and have a good day.